Good morning, students. As we promised, today we shall test the three rectifiers. We have learned the working principle and various performance characteristics of the three basic rectifiers, that is, half-wave rectifier, full-wave rectifier, and bridge rectifier. Today we shall actually test them. First, we are in a half-wave rectifier where you can see this is the transformer. I hope you can see my cursor. And this is a single diode, and this is the resistor, load resistor RL, right? Now I have set the RMS voltage of this source such that the peak-to-peak voltage at the secondary is 10 volt, which is equal to VM 10 volt. Because if we make it 10 volt, calculation becomes easier. Now, there is a multimeter to measure the voltage output. One multimeter is measuring the DC. This is the left-hand side one. And the right multimeter is measuring the AC component. Of course, you could use only one multimeter and toggle them. But to show you simultaneously the two readings, I have used two multimeters. And there is an oscilloscope. Here, the channel A of the oscilloscope, this red line is connected to the secondary of the transformer, that is full wave input. And the blue line, channel B, is connected to the output, which is half-wave rectified. Now, let us run it and you will see how it works, right? So, we start the simulation. Simulation is running. We stop it. You see, the red line here is a full wave line. That means transformer secondary is full wave, and transformer and the load resistance or the potential at the load after the diode is only half wave. This blue line is only half wave, right? That is exactly what we desired also. Now, if your VM is 10 volt, then as per our theoretical calculation, VDC is VM by pi, it should be 3.18 volt. What you the DC voltage is 2.87 volt. It is little less. Why it is little less? This point we have not discussed in our theoretical lecture. Also, it is normally, I have found, not mentioned in your textbooks. It is because of this diode drop. Some amount of voltage drops across this diode, which you have learned in your basic device subject. And that diode drop for germanium, it is 0.6. For silicon, it is 0.2. And normally, it is around 0.7 volt. In the oscilloscope diagram also, I think you can see that blue line, half wave, its peak is little less than the red line half wave. That is because of the diode drop. And that is why VDC is also, instead of 3.81 volt, we got 2.87 volt. Anyway, it is very near to the theoretical value. And as per our calculation of half-wave rectifier, VAC is the ripple factor multiplied by VDC, which is 1.21 multiplied by 3.18. This value, it is 3.85 volt, where we are getting 3.585 volt. So what we finally get, as we learned in our theoretical lecture, the AC component of a half-wave rectifier is larger than the DC component. So, though it provides a DC, but it provides too much of AC, which is harmful to our equipment, which is connected to this rectifier. As I promised, later on we shall also learn how to filter out this AC component. So AC component will become much less. So this is the half-wave rectifier. Now let's go to the full-wave rectifier. This is a full-wave rectifier, right? Here, this is the transformer. As we said, there are two secondaries, right? And there is a center tap. Once again, I have taken VM to be 10 volt, so that VDC, as per theoretical calculation, is 6.37 volt. And VAC, as per theoretical calculation, is much less than the DC, 3.07 volt. Similarly, there are two multimeters and an oscilloscope connected. Let us run this program, see it's running, and now it's stop it. Here you find that this is the full wave rectification voltage, full wave rectification, sorry, this is the full wave inputs transformer secondary, but the output to the load is rectified full wave. That means there is a positive half cycle at the output for the negative half cycle of the input. Also for the positive half cycle for the input, there is a blue line. That is the full wave rectification, rectified wave. Once again, there is a small difference between the peak values. That is because of the diode drop. Now here, our theoretical value of VDC was 6.37 volt. We got 5.74 volt, right? 6.37 minus 5.3474 is something around zero point 0.6 or zero point 0.7 volt. That is because of the drop in the diode. And AC voltage was supposed to be 3.07. We got 3.04 volt. So this we find that the test value of these rectifiers are very close to our theoretical values. Then we go to bridge rectifier. Bridge rectifier, you see, transformer is again 1:1 single secondary transformer. There are 4 diodes, as we have learned in our theoretical class. Similarly, I have used 2 multimeters and I have used oscilloscope. The red line is connected to the input, secondary input, and blue line is to the output. Here, once again, VM is 10 volt. As per our theoretical calculation, VDC should be 6.37 and VAC 0.07 because these two values are same as the full wave rectifier because it is the same output waveform. Once again, if we run it, you see it starts running and then stop it. See the waveform. There is a red line is the transformer secondary waveform, full wave waveform, and the blue line is the rectified waveform. Here you find, please note, that the difference between the red peak and the blue peak is more than the earlier one. That is because here the circuit gets completed by 2 diodes. That means diode drop will be around 1.5 volt approximately, depends upon the type of the diode. So VDC 6.37, we got 5.04. That means about 1.4 volt less than the theoretical value. VAC was supposed to be 3.07 volt. We got 2.934 volt. So this is how the 3 rectifiers work. I would suggest that this software you have in your college, and this is and you can also download educational version and student version. You learn a new circuit, just simulate it and have a real hands-on feeling. Okay, so we close our class today here, and I have a humble request, and if you feel like, my request is if you could please subscribe to my channel. That gives me a lot of enthusiasm to do this hard work for you. Anyway, thank you very much.